Okay, and I'm Dave Oswald. I run Salt Lake Perl Mongers. I'm a developer. I usually use Perl. Sometimes I use C++ or some of the other tools that are available out there, just depending on what's needed. And I wanted to do a little shameless plug. Salt Lake Perl Mongers has meetings similar to this, but more Perl oriented. And we meet in Draper, so it's not all that far for people from Orem and Provo. We meet typically the second Tuesday each month. Has anybody here been to a Perl Mongers meeting? I have, Doran has. That's about it. So.
It's usually not just us.
yeah. Usually Doran and I just sit there and talk to each other. No, we've
had up to 20 people there. So.
Yeah, up to 20 at the normal meetings, and we've had some presentations like from Damian Conway with where we had over 100 people, I think, there. So. Has anybody seen this cartoon before? This is a little bit tongue-in-cheek, so let's change this. Let's see. This is not our goal today. We're not going to learn how to save the world with regular expressions. In fact, we're going to learn that there are times when they're completely inappropriate to use. We're also going to learn that they're pretty convenient. They can be fun. I apologize in advance. I'm not going to apologize. Examples will be in Perl. Why? Because Perl regular expressions are part of Perl's syntax. They're very convenient to use. If I were to base this on C++11 regular expressions, it would be a disaster because we spend all of our time dealing with how to incorporate them into code. With Perl, they're kind of automatically a part of code. So, and because I get to use some cool tools, one of which you'll get to see this evening. It really doesn't matter what language we present regular expressions in, because the concepts, although the syntaxes will differ, the concepts are going to be the same. And it'll be okay. Okay, some definitions. Now, before we start off here, I just want to let you know, my assumption is that in this room there are people who are extremely advanced in using regular expressions, that there are also people who are intimidated by them, and I myself kind of fall somewhere in between. And so it reminds me, when I went to the University of Utah, and I played in the jazz band for my first couple of years there, and our band professor one time said there was a story about a guy who was just an excellent trombone player. And he was hired to do a recording. He was hired for a recording studio, and he walked in to the recording studio and he just sat down in the lead chair. What he didn't realize is that the entire recording was by trombone players, and that many of the greatest trombone players in the world were also there. And it took him a while to get another gig. And so I'm not going to make the assumption that I know more than anybody here. I probably know more than a couple, and I know a lot less than most of you probably. And we'll just go with that. So, a few definitions right up front. Regular expressions can within their patterns represent literal characters. There are some meta characters which give other characters special meanings. There are meta symbols which can represent various things. And then there are operators. And in Perl, we're going to look at the Perl operators matching, substitution, and the binding operators, which are used to bind strings or text or whatever to the operators to perform the matches. Anytime you want to give a literal character special meaning, you'll put a backslash in front of it. And just about any time that you want to give a meta character literal meaning, you'll put a backslash in front of it. And if you want to give a backslash literal meaning, then you'll put a backslash in front of that too, which is similar to strings in most languages. So just for a quick trivial example, so that we can get kind of the Perl syntax part of it behind us, we're going to take a string here, assign to it a literal, just another Perl hacker, and here we're going to test if this matches this pattern. And so we're binding the string using the binding operator to the regular expression operator. And the output here will be match. That's starting off real basic. And we'll just look at some syntactic shortcuts, which will make it easier for us to go through the rest of the discussion. Here we're going to assign just another Perl hacker to what Perl considers its topic variable, or the it variable. And if we do that, then we no longer have to worry about binding. This is implicitly bound to our regular expression operator. Another convenience, another syntactic sugar in Perl is that you don't have to put the little m in front of your operator. As long as you're using standard delimiters, you can forego that. And so just for simplicity's sake, we've taken, say, match if string binds and matches m/Perl/, and we can take out a lot of that just by assigning directly to the implicit it variable. Now we're going to get into the more heavy-duty stuff. Has anybody heard these terms, NFA, DFA? Yeah. Lua uses deterministic finite automata, right? Most of the other languages that we're familiar with, certainly most of the scripting languages, use NFA engines. And we'll talk for a moment about what those are. The regular expression engine falls into one of two categories, and we're going to use these categories or these terms fairly loosely because, strictly speaking, it's hard to find a pure NFA implementation or a pure DFA implementation. Deterministic finite automata, probably the easiest way to explain it is that it's a text-directed match. The text, at any given point, it's the engine's job to know where it is within the string and to know what all of the possibilities are from that point forward, essentially, or what all of the remaining possibilities are. With the non-deterministic finite automata, which is what most of us use in our day-to-day use with regular expressions, it's a regular expression-directed match, where the expression directs where we are in the string and can do backtracking and some other more fancy things. Lex, I think Lua should be on this list as far as languages that use DFA. DFA will typically be a more simple regular expression. Deterministic finite automata doesn't allow for things like, typically like back references, look behind assertions, whereas non-deterministic finite automata engines allow for backtracking and some more flexible semantics. And that's what we find in Emacs, in Java, grep, less, more, net, Perl-compatible regular expression library, which shows up everywhere, including PHP, Perl itself, Python, Ruby, Sed, V, and C++ 11 now has that incorporated as well. So our focus tonight will be on NFA engines, but a lot of what we discuss will still be applicable to DFA engines, except for the parts about backtracking and look behind. There are two big rules with NFA engines. The first rule is that the match that begins the earliest wins, the earliest in the string. And the second is that standard quantifiers are greedy. So now we get to look at one of the fun tools, if I can make this work right. Here we go. Okay.
This is Damien Conway's.
Yeah, have you seen this? This is...
I did a presentation on it.
Oh, did you? Okay, so most people here have seen it.
No, it's been a while.
Oh, okay. Good. Well, let's take a look at it here. So we're going to do... Just make sure I'm in the right place. It's going to be hard to kind of jump back and forth between slides, but we're going to enter a regular expression to use, and we're going to enter a string. This is an example that I took out of Mastering Regular Expressions. So And now we can look at how this is going to match. And remember, we're looking at the two rules. The first rule being that that the first thing to match wins typically.
At the beginning, when I mentioned that I've seen whole programs written in regular expressions.
Mm-hmm.
This is what I was talking about.
Yeah, this is a mess.
This entire program is a giant regular expression.
We're going to step through. Oops. As I step through, you're going to see at the bottom, it's pointing to where it's looking in the string. And at the top, it's going to be pointing to at what it's trying to match. So it's trying to match, it's trying to see if the letter H will match 2. Failed. Now we've moved on to O. You see the little pointer at the bottom is advanced. Now we look at T. Oh, T might match, right? And so now it's going to try to match the O. Again, that fails. Space isn't going to match. Now we got a TO again. Oh, we're doing good. But it's matching in the wrong place, right? The wrong part of the pattern is matching. So now it wants to start capturing. It's going to try to match night. That's going to fail. So what does it do? Tries the next alternative. Night also fails. And now it's going to try the next alternative. Still fails. Now it backtracks. We go back to the start of the regular expression, and we keep moving on. We'll move on a little further. Now it's found another TO in the string there. And we're going to look through the string one more time. Well, night fails. KNIGHT fails. Matched. So we found the match in 52 steps within the regular expression engine. So let me find my place in my slides again. Oops. Well, we're going to have to do this tonight, huh? Okay. So as we just saw, first it tries to match the TO in tonic with night, night, night. Then it backtracked and advanced the position within the string to the next. It keeps advancing, advancing, advancing. And then finally it gets to the right point where it has TO, NIGHT, and it can match your TO and your NIGHT, and it's happy. So backtracking is a feature that is common in non-deterministic finite automata expression engines. And it's kind of a recursive process. It's really a matter of leaving breadcrumbs. When it gets to this point in the pattern here, for example, in the string tonic, it's at this point in the pattern, and it leaves a breadcrumb here. It leaves a little marker here, knowing I'm going to have to come back maybe and revisit this. And then it compares night, and that doesn't work, and so it tries this, and that doesn't work. Tries this, that still doesn't work. So it backtracks. It knows, it goes back to where it left its little marker and says, well, let's try another decision. Let's advance a little further and find another 2, and then it goes on from there. So that's backtracking. Backtracking could be kind of a problem. In this example here, 2 dot star is going to consume the entire string, starting here all the way to the end, right? But we're also requiring that this part match. This is not optional. It also has to match or not to be. So that really means that what we want in the end is to end up with 2 dot star matching to be, comma, space, and then all of the rest going into or not to be. Well, how do we get there? The dot star is a greedy quantifier. That's going to, like I said before, match the entire thing. So let's exit out of this again and take a look at what the regex doctor says to us. So now we'll give it the string to be. And we'll give it the pattern. Did I type that right? So now we'll step through that. So now it's captured the entire thing. These capturing parentheses have captured the entire string there. That's not going to match in the end, because this has to match also. So let's step a little farther forward and see what happens. Now it gets to this next part. Failed. It fails because there's nothing left. Our string, we've already advanced the pointer to the very end of our string. We've already captured everything into this part. That portion of the regular expression has failed on this attempt. So what's going to happen? We're going to backtrack, and we're going to give up a little. You see here the marker has moved back one character. So now we're only trying to match, now we're only trying to capture into here to be or not to b. Yeah. And if we keep going, it's going to keep moving the pointer back one, giving up a little bit each time from the first capture because of that greedy quantifier until it gets to the point, let's see here. Where it can now capture the remaining part. And in 83 steps, we've moved all the way forward through the string, and then we've moved back through the string, given back some of this string so that this second quantifier, or so that this second portion of the pattern can also match and capture what it needs to. Yeah?
So things in parentheses always get numbered variables. What are those called?
In Perl, they do. They get numbered variables. They're called numbered captures. You can do named captures as well in Perl, but the most trivial syntax is to use numbered captures. So.
What is that program called that you're running?
This is called RxRx, and it's actually a module from Damian Conway. If you were to go to CPAN for Perl, the module is called regex debugger, regex::debugger. And if you install that module, it automatically installs this little executable as well to make it run.
It's RxRx.
RxRx is the executable, yeah. It's pretty cool, isn't it? Yeah.
It is.
Yeah. And you can step backwards too. I'm not sure once it's matched. Yeah, see, I can go backwards because I didn't catch something.
You can fast forward.
Yeah, if I hit C, it'll just keep going until it gets to the end. Yeah.
There's a whole bunch of options.
So now we'll go back to. I wonder if there's a start slideshow from current slide. Nope, looks like first slide is my option here.
If you go out to the list of slides, you can click on the one.
Oh yeah, you're probably right. Yeah, good idea. I'll do that next time. Okay. So what we did is we forced greedy quantifier, this dot star, which tried to capture everything, consume everything. We forced it to give things up, and it only gives it up little by little, one step at a time. So 12 times it backtracked to the start of the pattern and gave up a little bit more each time. Yeah.
Can you explain the dot star?
Dot star is okay. Dot is a meta character which will match anything except for new line, and star is a greedy quantifier. A quantifier says that it can match a number of times, more than one time, and the star in specific, as quantifiers go, means that it can match 0 or more times. So literally, we could this little sub expression here, if all this were gone, if it were only given just this much of the string, just 2, it could still match 2, because dot star means it can match 0 or it can match any characters 0 or more times. So does that explain it? Yeah. So now, backtracking can really get nasty. And this is an example where you and I can look at this and see, now this is what's called a negated character class here. We're saying that this string cannot contain any letter B's at the end of the string, okay? This match is destined to fail, because here's our string, and here at the end the string cannot have a B. And so this match is destined to fail. We can look at that and just like that say, that's going to fail. However, the regular expression engine doesn't look all the way to the end of the string and see what's happening. It looks here and says, well, we can match any number of A's, and we can do that any number of times. So it's kind of an ambiguous construct to begin with. And let's see what happens if we feed that to the regex doctor. Okay. So the string is, oops. And the regular expression just to explain the regular expression again, here we have the letter A, literal, which can repeat 0 or more times. And that's a captured group, and that whole construct can repeat 0 or more times. But at the end of the string, you cannot have, because this is a character class, you cannot have either a capital or lowercase b. This caret here means to negate the character class. And then this anchors us to the very end of the string. Here we have a string that ends in a b, so it's destined to fail. Let me just run through it real fast. Oops. Look at all the backtracking that's happening here. 213 steps to get to the end there. And it still failed. Now a DFA engine would know immediately that it had failed. Yeah. Did you have a question?
So the brackets mean the character class and
yeah, the square brackets mean character class, and the caret symbol means to negate the character class.
okay, because I'm used to the caret meaning the beginning of the string.
It would mean that, it would have that semantics if it were not inside of a character class. If it were outside of, and you put it up here, then it would mean at the beginning of the string. And I think if you put it anywhere else in your pattern, then it has no meaning other than its literal self.
And even in the character class,
it only has.
time it has a meaning if it's the first.
That's right. Yeah, character classes have weird rules. For example, you can create a range A-Z, and you've got a range. But if you have AZ with a hyphen at the end, then the hyphen means the literal hyphen in a character class.
Hyphens,
so.
if you want a literal hyphen, it has to be at the end.
Or the beginning.
Or the beginning.
Yeah.
So if you have a caret by itself in a character class, is that just a caret, or does it mean anything?
Negated nothing. I don't know. We'd have to try it. Yeah. Negated nothing. That means it can match anything, right? I don't know. Yeah.
So, in the other type of engine that doesn't support backtracking, would your first example have failed? Like with the, it was like an A dot asterisk and then some kind of ending character, would that fail?
So what you're talking about this string with this string would still fail, but it would fail much faster.
The previous example.
Oh, the previous example where it was to be or not to be, right? Is that? Right. Yeah, that one would not fail. It would still pass because what happens with a DFA engine is that it essentially studies the regular expression and spends more time in compilation so that it knows what all of the possible branches are going to be when it puts the string to it. It's more time in compilation, but its running time is generally O1, well, ON for the length of the string. Yeah. But and so that would seem like, well, that's wonderful, that's fantastic. We can do matches in linear time instead of this turned into more than quadratic time here, right? That seems great, except that one compilation takes longer, and so in an interpreted language, that's not going to do you much good. And then the second thing is, it doesn't allow for any back references, so you could never refer to this capture group within your own regular expression. So you can't match an X and then refer back to what that match was within the regular expression, and you also can't do look behinds. So there are some things you give up for the simplicity and the speed that it provides. Yeah.
Also, I think in Java, when they do the backtracking stuff, you can execute arbitrary pieces of code.
Yeah.
Back in there, and I imagine Perl can do the same.
Yeah. Well, and
that's where they got it from.
Yeah. and you don't. And maybe that's a feature.
In regular expressions, it came from Perl.
pretty much. And that's why I don't feel so bad presenting in Perl, because even if whatever language you prefer doesn't have this particular construct, it's going to eventually. And Perl steals.
Or you can link to the library that already has it.
Yeah, exactly.
You just link to the PCRE library.
Yeah, and there it is.
It.
And so I think it was Mastering Perl, the book by Brian Foy, that mentions that anything that's in the Perl regular expression library, somebody else, at some point in time, something forked off of that. And that's, the PCRE may have forked off a generation earlier, but then it's still pulling the new changes in. And maybe Python comes up with something that Perl hasn't got yet. Well, in a newer version of Perl, it'll show up in Perl too. We all kind of steal from each other. But anyway, the point to this was that we went through 213 steps just to fail. It wasn't very efficient.
What I was saying though is that if it's like a logical extension to regular expressions, then it probably came from another language. But if it's like some
Crazy.
bizarre, crazy,
Yeah, it came from Perl. Usually if it's bizarre and crazy, that's probably the case. Okay, so let's see here. Yeah, I don't know.
This example is sort of, for me, a metaphor for using Perl. A lot of work just to fail. So.
See, and for me, I went straight to Perl to give the discussion because I could get more done more quickly. That's funny, just to fail. Let's see. I don't see any option to start from current slide. There we go. There we go. So the regex failed in 213 steps. Now to get it under control, we're going to change one thing here. We're going to add to it a plus after the quantifier. This makes the quantifier possessive. And what that means is that that this particular quantifier will not backtrack. That means that this one still can backtrack a few times. It'll consume everything and then it'll back off 12 steps or however many steps. But this one cannot. And so now our regex will fail after 79 steps instead of 213. Other possessive quantifiers. So first of all, the star quantifier means that you can match 0 or more times. The plus quantifier means 1 or more times. The question mark quantifier means that it can match 0 or 1 times. A bracketed quantifier means that it can match a minimum of n and a maximum of m. And you can leave off either one of those to have no minimum or to have no maximum. Or you could have just a single number in there. It has to match exactly n times. By putting a plus after any of those, they become possessive. No backtracking can occur within that atom or within that subexpression. Possessive quantifiers. Where that's useful is in, you can carefully construct a regular expression to fail more quickly with a string that it would have failed with anyway. So, an extreme example. I'm not going to put this into the regex doctor because. So here we have a string of A's that's 64 characters long, 64 A's in a row, and here we have I think it's 32 A stars, and then it has to match a BB at the end, and there's no B at the end of this string, so it has to fail. We can look at it and know it's going to have to fail. You're going to kill the process before you ever get to. In fact, the universe will collapse or expand beyond, and all heat will be lost, whichever actually ends up happening billions of years in the future, before this ever ends. By making it a possessive quantifier. So here's another way of constructing a possessive quantifier. We're going to change this. We're going to change the star at the end to a possessive quantifier. Now it has to end in 4,550 iterations. So one of the kind of rules of thumb that we think of in regular expressions is that the longest leftmost will be what's consumed in a match. The longest thing that can possibly match, farthest left in the string as possible that can possibly match, that's what's going to match. Not always, though. We can look at one self-sufficient. Is it going to match oneself here? This part here doesn't have to match. This part here, this self here, doesn't have to match. It could match one and then self-sufficient. Let's look at what it actually does. Sorry, I have to advance to the right slide so I'm typing correctly. Okay. And then the string will be so the first thing it's going to try to do is find a 1, because that's a literal, it has to match that somewhere. And it found one, great. Now it's going to capture into the regex variable 1, and it's going to try to capture self, and it matched. And now we're done there. Capture 2. That's gonna, that part failed, and so we have only matched this portion of the string, one self. So longest leftmost doesn't necessarily always happen. In this case, one self is shorter than one self-sufficient being captured separately. If longest leftmost were always applicable, you would have no capture in 1, and in 2 you would have self-sufficient, and that didn't happen here. So now greedy and lazy. We said before that the star quantifier is greedy, so by adding a question mark after it, it makes it lazy, which means that it doesn't try to match as much as possible. So with the greedy quantifier, dot star is automatically going to attempt to match everything, and then as we move through our match, it's going to slowly give up characters until enough is left over for foo to match literally, right? With a lazy quantifier, then first only I is going to match, and that's not enough. So then I, and a little bit more, is going to keep advancing until it gets to the foo. We can look at both of those real quick. These are both going to match, but they're going to do so differently. So here's first with the greedy matching. It just matched everything. This little dot star has now grabbed the entire string, right? But that can't be a successful match because we haven't matched foo. So we have to give something back. See, it failed. It's going to backtrack, and it gave up the last O. Still fails. Going to backtrack again, give up the next O. Still failed. Backtrack again, and now it can match the literal foo as well. Matched. 14 steps. So now let's look at the same thing, but with a different regular expression. So now instead of trying to match the entire string, and instead of trying to capture the entire string with this quantifier, we now have a lazy quantifier that's only going to capture the minimal amount. It captured I. Well, that's not enough because it hasn't reached foo yet. Can't match foo yet. Failed. Backtracks. Now it's going to keep moving the pointer at the bottom forward in the string instead of backward in the string until finally it gets to foo. That matches, and now in 26 steps we've matched. Does that make sense? Let's see. Start slides from the same point. Other examples. We're going to try to match this word, camel case, with a capitalization in the middle, and we're going to use kind of a contrived regular expression. The first one uses, we think, well, if I use a greedy quantifier, that's not going to work for me because it's going to try to capture the entire I should have put in, this should be a case-insensitive match. But anyway, oh yeah, this works. It's going to try to capture the entire thing. First it's going to match the C, and then this dot star is going to match everything else if it's greedy, right? So I know how to solve that. Let's go with a lazy quantifier. This one's only going to match the C, and then it's going to try to match just the first A, right? And that'll be great, because then it'll move forward through the string until you get to the C, and then the second part of my regular expression here can match that C, and it's also going to be lazy, or it's going to be optional, but because in our example, case might not be there. Anyway, camel case, the problem is going to be that whether it's lazy or greedy, it still doesn't know where to give up and to give some back. This second part here being optional isn't going to match, and so your capture is only going to be, out of all this, the only thing that's captured is going to be the C, because that's the only part of it that has to happen. If you use a lazy quantifier, you really have to force the next part of your match to occur, or else it's not going to capture, or it's not going to match as much as you think it should, right? Well, so that's a gotcha. Well, let's try something else. Let's make it greedy instead, because obviously being lazy didn't work for us. Let's try being greedy. Now instead it's going to capture the entire thing, and when we get to the second part, which is optional, it doesn't have to give anything back, because the second part is optional. So again, another gotcha. You've got to force your quantifiers to capture exactly how much you want them to catch. Here's one that actually works. We're going to capture A through Z followed by anything that's not A through Z uppercase. We're going to, in other words, we can capture lowercase letters, as much of those as possible. And then the next time we get to a capital, then we know that we're moving on to the second sub-expression. So now by being very explicit in what we are allowed to match in our first expression, the second sub-expression has something left over to still work with. And so that one works. And I say kind of because you would never match an identifier that way, but it works for this example. My point was trying to show that a lot of times you can really get yourself into trouble saying, why isn't this thing matching like I think it's supposed to match? And I'm using a lazy quantifier. It ought to be matching, but unless you force it to know exactly where it's supposed to make that cutoff, it's going to match as little as possible or as much as possible. Okay. We'll go through the 6 more NFA rules real fast before we get on to other things. Matches occur as far left as possible. We've seen that in a few of our examples. So the first thing in the string to start to match is if it can make a successful match throughout the rest of your pattern, that first thing that it found is going to be what it goes with. DFA might be a little different. DFA typically will go with the longest, I think, although I'm not 100% sure on that. Alternation has left to right precedence. So if you have 3 options, night, night, and night, spelled differently. The first one listed in the alternate, and all 3 of them could match. The first one listed in the alternation will be the one that actually does match. Any alternative matches if every item listed in the alternative matches sequentially such that the entire regular expression is satisfied. That's just basically saying that the pattern follows its rules. It has to, literals have to match, everything has to match sequentially. If an assertion doesn't match, backtracking occurs to try higher pecking order assertions with different choices. So in the example of A star and then in parentheses another star, the outer star is higher precedence, the inner star is lower precedence. It'll iterate through all of the possible inner A stars before it goes and changes the number of quantities in the outer A star. And so it's essentially a permutation type of an algorithm, recursive permutation algorithm is how it works. Quantifiers must be satisfied within their permissible range. If you specify 0 or more, then you're really going to get 0 or more. And each atom matches according to its designated semantics. If it fails, the engine backtracks, twiddles the atom's quantifier within the quantifier's permissible range. So that's how NFA works. One thing that we can learn by all of the complexities of quantifiers and meta-characters is that it's often quite a lot easier to simply break your regular expression down into smaller patterns and allow the programming language itself to handle the logic, right? So here we're going to test the string if Brian and John, if they both exist in this string. And this one matches, this one's fine. The one way to write that in a single regular expression is using alternation, but then you have to see if Brian and then dot star John, or if John dot star Brian. If either of these patterns match, you've just repeated yourself, you've done twice as much work as you need to do, and you're going to get into some backtracking along the way, not as efficient. It's not as efficient in programmer time, and it's not as efficient in runtime. So keep your expressions as simple as possible. This one's fun, progressive matching. This one took a while for me to get figured out. Let's look at a tic-tac-toe board. Anybody with a C background knows that a multidimensional array really is just a one-dimensional array with multidimensional semantics applied to it, right? And so we can take this multidimensional array and turn it into a string, and now it's become a pattern, really. It's become a pattern that we can search for a solution. So what are we going to do? First, we're going to test if we're going to match any three things here, dot, 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 but we're going to capture the first one that we match. We're going to capture that first x by using the G modifier at the end of our regular expression. And I know this is Perl syntax, but it exists within PCRE as well. Every language has a way of doing global matches. If you use the G modifier, then your position does not your match position in the string does not reset at the end of the match. And so now that we've matched in this first pattern the first three characters here, x, x, o, our second pattern is going to go on and match the next three. And we're going to force that by using an assertion. This /g assertion is telling this next pattern to start where the previous pattern left off. So the previous pattern wiped out these 3 digits for us. The next pattern is going to test the next 3 digits by using that g assertion. And what's it going to look for? It's going to look to see if what it captured in the first expression is present in the second position in the next 3. And then we're going to use the G assertion again to start on the last 3 digits, and again to test if what was captured in the second expression is present as the third character in the third expression. So here we're going to look for an x here, an x in the middle here, and an x at the end here. And if we have those 3, then we have a winner. One wins. X wins. It's kind of a contrived example, but it actually works for that. Tic-tac-toe. Let's look at a regular expression, a pure regular expression solution to seeing if a tic-tac-toe board has a winner. So here we have a tic-tac-toe board where 2 positions haven't been played. We have x, nothing played there, a couple of O's and x, but if we look at it as the 3 segments, x in the first, x in the middle, x in the last, we have a diagonal win. Now we're going to use some syntax that's unique to Perl. However, it would not surprise me if something similar to this has turned up already in PCRE, in Python. I don't know, but it wouldn't surprise me. We're going to define a little subroutine here. And our subroutine is simply, we made a real simple subroutine, which is just a character class, just to make it real simple. A character class that can match X or O. And we're going to call that subroutine mark. And so now we're going to go through and capture any given mark, either an X or an O, and then see if a particular pattern applies. So if mark followed by the same mark followed by the same mark applies at the beginning of any row, then we have a row win, a row-wise win. Here, if we have the mark followed by 2 of anything else, followed by the mark again, followed by 2 of anything else, followed by the mark again, now we have a column, and it can be any column that won. Here we have a forward diagonal, and here we have a reverse diagonal. And so this can determine if there is a winner in a given tic-tac-toe board. It won't tell you who got there first. You have to test them individually as they put their moves in.
It looks to me like unplayed will win the game at the very beginning.
Unplayed will win. These two here.
Yeah.
Yeah.
No, at the beginning it will all be unplayed.
Oh yeah, we all unplayed. Yeah, that's right. Yeah, you're right, because I'm not. I validate that outside of Perl, or outside of a regular expression. I have a module that does it actually, just for fun.
But if you made the first one capture just X or O, then
Yeah, that should be good.
Yeah. Okay, extended bracketed character classes. This is something that's new in Perl. And again, I don't know if it's been implemented in other languages. Perl could have stolen it from another language for all I know. But this is one of the problems that I've always had with character classes is that you can have positive character classes, you can have negated character classes, but you can't have combinations. You can't have what we would call set theory. You can't have sets where you exclude, where you take unions, intersections. Well, now you can. With this syntax here, you've created a character class. This character class will now include all Unicode tie characters and all Unicode digit characters with the and. This one will include all Unicode tie or all Unicode lao. This one here will include all A through Z except for the vowels. So now we have intersections, unions, subtraction, symmetric difference, and complement available in character classes. And that's new, and I haven't played with it as much as I'd like, but it's bound to be fun. So where should we use regular expressions? It should be obvious that we don't want to spend too much time messing with a regular expression. They can be fragile, they can be difficult, so we should not parse HTML with regular expressions, except that, I'd like to look at this. Tom Christiansen, who is one of the authors of Programming Perl and a few other books, actually wrote a capable and complete HTML parser in Perl's extended regular expressions. And then he went on to say, we'll see in a minute what he went on to say. Randall Schwartz wrote a JSON parser, which you can look at on Perl Monks, completely in regular expressions, again, extended regular expressions. It is possible. None of them will ever tell you that it's a great idea. Email addresses. Don't waste your time. Mastering regular expressions, the first edition demonstrates a regular expression matching, a regular expression that matches RFC compliant regular expressions, email addresses. It wasn't fully compliant, and it was omitted from the second and third editions because it couldn't be made compliant.
Wrong tool.
Right, wrong tool. Regular expressions are not for parsing HTML. You might use them for parsing components. You might use them for identifying a tag or something. You don't use them for parsing HTML. You don't use them for parsing JSON. You don't use them for parsing email addresses. You use them for small tasks. This is what Tom Christiansen has to say about, after he wrote the HTML parser, optimal for small HTML parsing problems, pessimal for large ones. Much, much harder than almost anyone ever thinks it is. That's probably even an understatement. Too much is probably an understatement. And this one, I think, is really the gem. You'll eventually reach a point where you have to work harder to affect a solution that uses regexes than you would have to using a parsing class. When you get to a point where you realize this regular expression has grown too fragile, too unwieldy, too big, and has wasted too much of my time, then you probably ought to be looking at a parsing class of some sort. Even if it's possible, which it probably could be with modern, modern adaptations on regular expressions. It gets to a point where it's not worth it.
It's often not that big.
Yeah. Yeah, regular expressions don't have to grow that big before they become fragile. Is that what you mean?
Yeah.
Yeah, it doesn't take much. That's why earlier we talked about break them up into smaller components if you can.
Yeah.
So.
Well, and Perl has, I don't think most other languages can do that, where the spaces don't count as...
Oh yeah, where you put the X...
You had that on the previous slide.
Yeah, if you use the X modifier at the end of a regular expression, then it becomes freeform. The white space doesn't count in the match.
Which makes it easier to...
Yeah, and Perl also allows you to name your captures and to define subroutines. It's grown to the point that you can actually define a grammar in a regular expression in Perl, but it's still not a good idea. So it still takes too much work. Has anybody seen this one on Stack Overflow? I thought that one's hilarious. I'll give you a second. This was somebody's fed up rant to people asking about how to parse HTML. It gets more goofy as it goes. So. That's good enough for now. Okay, appropriate alternatives. For complex grammars, use parsing classes. You know, every language has something for parsing HTML, for parsing XML, JSON, whatever. Every language has something. Fixed width fields. If you have fixed width fields in your text, then a regular expression is not the optimal tool. Perl has unpack. Every language has subster of some sort. That's a more optimal tool. Comma separated values. Stop trying to use regular expressions for comma separated values. I should have added on here also balanced text. Any text.
Just say actually just stop using comma separated values.
Yeah, that would be better. Yeah.
Say don't parse.
Just don't use them. Except that everybody's always trying to do something with spreadsheets, and spreadsheets dump to CSV so easily. But it's, yeah, use a library. And I should have put on there balanced text. Every language ought to have something for dealing with balanced text, which would mean text in quotes, text in brackets, in parentheses. Don't try to do that with regular expressions. It is probably possible, but it's not worth your time as a programmer. It's supposed to be fun, and it's not fun when you have to start doing that.
Not to include the memory load.
Yeah, the memory load, the backtracking is not the most efficient way. Yeah, there's a lot of reasons. If you have uncomplicated, predictable data, then use a regular expression and use them prolifically. So that's everything I have to say for this evening. These are some references that I use. Programming Perl, the 4th edition, has a chapter on regular expressions and another chapter that's excellent on Unicode. And although it's a Perl book, a lot of what it discusses in regular expressions and also in the Unicode section are some of the best resources you'll find anywhere for learning, especially about Unicode. Mastering Regular Expressions, that used to be in the 1st edition a Perl-only book, but now it's expanded to include Java and PHP, and I think Python is in there, Sed and Awk. That is the best book anywhere. Even though it was written, I think the most recent edition in 2005, it's still the best book anywhere on learning regular expressions. Mastering Perl, the 2nd edition, has a chapter that's pretty good on some of the more esoteric functions of regular expressions in Perl. The regex debugger. Even if you're not a Perl user, if you're using Linux, you've got Perl on your system and you can install the regex debugger. Just go to CPAN. I don't know if it's been put into an RPM or anything like that yet.
It has. I just installed it over here.
There you go.
Apt-get, but I had to do lib, debugger, Perl,
Okay.
dashes to get in.
To get it, okay.
Yes.
But you were able to get it, see, right while we were talking. Regex debugger is great. Even though it uses Perl syntax regular expressions, you'll eventually become familiar enough with them that you can kind of think back and forth into whatever language you prefer. And, yes?
Don't most languages use Perl, like the Perl compatible regular expressions?
Yeah, most of the regular expressions that are out there are the...
PHP does.
Yeah, PHP does.
They used to have something else, but that's all deprecated.
Yeah, the basic core functions are going to be almost the same from language to language. I think grep might be a little different. Some of them will be different here or there. The core functionality will be very similar. It's when you get into the more way out there things like definitions and...
Unless you use VI.
Yeah, right. That'll be different too.
But there is a way to make VI use normal regular expression, or somewhat normal.
Is there?
Yeah. I got it from Damian Conway. He had some
way to do it?
One of his MRC stuff. He had
that would be
something that would
be
make
perfect.
the regular expressions in VI actually.
It would be perfect,
Same.
except that one of the reasons for using VI is that it's available everywhere you go.
Yeah.
And so then you sit down at somebody else's computer and now you've got to, I never learned how to do that.
What they, like how they were.
Just
Yeah.
V, you can do very magic
Yeah,
regular expressions,
Yeah.
and those ones are more Perl-like.
yeah,
And you can change it so that when you type a slash, it'll automatically put that V in there. And so just anytime
you have the very,
you're using them,
yeah,
you get the very magic ones.
cool.
So,
And then these are Perl documents, type Perl doc, Perl RE, Perl doc, Perl retut, or Perl doc, Perl RE care class. These are good resources, again, even like as we've said, the basics, most of what's in each of these documents will be applicable to any language that uses Perl compatible regular expressions. And they're probably the best resource available, at least for free online, for learning any of those, for learning those semantics and those syntaxes. So that's everything I've got. if anybody wants to play around with the regex doctor, we've got it installed on a couple systems at this point. Again, I'm Dave Oswald, and that's it. Thanks for having me.
Thank you, Dave.
You're welcome.